Internal incompressible viscous flow essentially means pipe flow, and Chapter 8 covers some of the most important material for fluid mechanics for the practicing engineer. In the first recorded lecture, we'll be talking about different pipe flow regimes, that is laminar and turbulent flow, and different regions of pipe flow, namely entrance and fully developed regions. And then we'll focus on laminar flow, first in a pipe and then in between parallel plates. Subsequent recordings we'll talk about turbulent flow and then the energy equation with the calculation of head loss and how that's used to solve pipe flow problems. Finally, we'll conclude with a summary of different flow measurement techniques. The flow could be classified as laminar or transitional or turbulent depending on the Reynolds number. In the case of low Reynolds numbers, we expect to see laminar flow. It's characterized by straight streamlines and relatively little mixing. Let's take a look at a video, and the video shows straight streamlines. Here's dye moving downstream in a circular pipe, and we see that the streamlines move straight, they're essentially steady, and there's very little diffusion that takes place in a laminar flow. In comparison to that, in a transitional flow, so right around a Reynolds number of 2300, we see that sometimes the flow is now unsteady. There are vortical regions in the flow that travel in sort of chunks. So sometimes the flow is straight like this and laminar, and then sometimes there's a lot of mixing, and so the characteristic shape of the streamline shows the effects of mixing and vorticity. So here's a chunk of turbulence moving downstream. So the turbulence is intermittent in the transitional flow. Finally, in turbulent flow, we see that the flow has a fair amount of vorticity and steadiness all of the time. This is unsteadiness in the velocity field, even though the flow rate itself is steady in this flow. So there are disturbances in the flow field that cause quite a bit of mixing, also cause more dissipation. And the pressure drop characteristics of the flow, as well as this mixing characteristic, is very different in turbulent versus laminar flow. If flow starts up from a reservoir over here on the left side and enters a pipe, especially with a smooth entrance as shown here, the flow is characterized by an almost blunt profile at a constant velocity. This is a flow that has inviscid characteristics, so at first you could consider neglecting the effects of viscosity in this flow. But what happens quickly as we move downstream is that we have the effects of the wall of the pipe, and viscosity tend to slow the flow down near the wall, and that's happening outside of this dotted line over here on either side. As we are close to the wall, viscosity slows down that fluid, and so we have a shear layer with a velocity gradient. And then in the center of the flow we continue to have a blunt flow profile. So we often call this an inviscid core, and this is a viscous region that characterize the entrance region in a pipe. Eventually these viscous regions grow to the point where they cross the center line, and soon thereafter the velocity profile has taken on a parabolic shape, illustrated here. And as we move further downstream, that velocity profile no longer changes. So the velocity profile is not a function of position in the pipe, whereas in the entrance region over here, as we move downstream, that velocity profile is constantly changing from blunt towards fully developed. The entrance region length can be characterized based on the Reynolds number if flow is laminar. That is, that the flow the entrance region, first of all, is proportional to the diameter of the pipe, and then it grows as you move downstream over the entrance length. It grows at about 5% of the Reynolds number. So, so this entrance region is longer and longer as flow rate increases, and therefore as Reynolds number increases. So that takes place up to the limits of laminar flow. If we have a turbulent flow, the entrance length is relatively fixed. That is not a function of Reynolds number, and turbulent flow develops fully within about 40 diameters, although some of the details of the turbulence might take twice as long to develop, but the velocity profile is developed within about 40 diameters in a turbulent flow. In fully developed flow, then, we assume, or actually we have observed, that the flow profile is independent of position downstream. So in this pipe illustration, we have a radial direction, and then we have our axial or flow direction. The flow profile is essentially just a function of lateral position, and as we move downstream, there's no difference in the flow profile between one station and the next and the next. This, as we see, will drive the condition that the pressure gradient in the flow field is constant, doesn't change with position. And the simplifications that come about to the Navier-Stokes equation in the case of fully developed flow mean that we can solve Navier-Stokes equation for a laminar flow situation. So that's what we'll do next. We're going to start by considering pipe flow. This is a little different order from the textbook, but I think it's the more important solution, or the one you'll be using the most. We consider flow at constant or steady flow rate Q of an incompressible fluid, so it follows the continuity equation. The flow is steady, that is, Q is steady in time, and in the case of laminar flow, the flow field will also be steady. We consider a Newtonian fluid, so one with a constant viscosity, and a flow that's axisymmetric, so it doesn't matter what angle we look at, it's the same flow field function of radial position. Furthermore, the flow does not have a swirling component, that is, there's no tangential flow component, and it's simply driven by a pressure gradient between the entrance of the pipe on the left-hand side and the exit here on the right-hand side, or by a height difference between those two, because gravity can drive the flow, or by a combination of those. So here's our velocity components: the axial velocity, which turns out to be the only component of velocity. We'll see that from the equations: radial and then tangential direction. Starting from the Navier-Stokes equation, which I've given you in the handout, we want to simplify based on the assumptions of fully developed flow. So to simplify the equation, we're going to start out with the assumption of steady flow, and that'll knock out the time derivatives in the momentum equation down here. By the way, this is the momentum equation written for cylindrical components. It's a little different from, and also continuity for cylindrical components, a little different from the Cartesian coordinate equations that we've seen before. There are a few extra derivatives because we're in cylindrical coordinates, but the simplifications that come about for pipe flow make these more complicated equations worthwhile to use. So as I was saying, we knock out the steady flow terms in the inertial side of the Navier-Stokes momentum equations, and then we consider that there's no swirl in the flow, and that knocks out all of the u theta terms. So up here in continuity, anything multiplied by u theta or containing u theta would drop out of the equations for non-swirling flow. In addition, then, we consider that the flow is axisymmetric. That means any derivatives of velocity with respect to theta direction can be crossed out. So we've got one here and we've got one over here, we've got one over here, over here. And then we consider the fully developed assumption, and that means that any derivatives of velocities with respect to x are 0. So here's dux dx is taken out of the equation, dur dx would be taken out of the equation. So any velocity derivative with respect to theta. And so you see we've dropped out quite a few terms from all four of these equations. Let's now focus on the continuity equation because we've only got one term left in the continuity equation. So I'm going to put this up here in the upper corner. Continuity is now essentially dr times ur dr is equal to 0, because we can cancel out the 1 over r term. So r u sub r is constant, or u sub r is a constant divided by the radial position. Now if we consider that 1 over r goes infinite when r is 0, but the velocity needs to be finite for a physically real flow, that means that the constant c here has to be 0, or that means radial velocity is 0. So in a fully developed flow we have no radial velocity, and if there's no swirl, then we're simply left with an axial velocity. If there was swirling flow, since it's axisymmetric, that would still drop out of this equation, so that would just mean that the swirling flow is constant. But again, that's something that we're assuming is not present in this flow. So if ur is 0, then fully developed flow allows us to cancel out some more terms, anything multiplied by ur in the Navier-Stokes equation. And so we see at this point in fully developed laminar flow that the entire left-hand side of each momentum equation is 0 in fully developed flow. So we have 0 equal to pressure gradient and viscous derivatives, and we don't have many of those left either. So let's continue now and summarize our simplified equations. We have the axial direction momentum equation, where we have the pressure gradient and one viscous derivative and a body force. And then in radial and tangential directions we simply have a balance between pressure gradient terms and body force. And as I said, flow is purely axial, so we're going to write the velocity u sub x, that axial flow velocity, as simply u. And u is not a function of theta because flow is axisymmetric. U is not a function of axial position because flow is fully developed, so we simply have u as a function of r, radial position. Other two components go to 0. Now we consider when force, body force F is gravitational, then the pressure field is simply a hydrostatic pressure field, that is pressure balanced against body force of gravity, pressure balanced against body force of gravity, same up here, plus the effects of the viscous gradient can go into dp dx. To simplify the equations, we will define something called the total hydrostatic pressure, P prime, and this is usually what we mean when someone analyzes flow and says let's ignore gravity. It means we're using this P prime variable. The hydrostatic pressure is defined so that the gradient of hydrostatic pressure is gradient of pressure minus rho times g, gravitational force. For example, if g was in the minus k direction, you would write P prime as then P plus rho gz, so that its gradient would give us the gradient of pressure minus a minus gk here for g, and then its gradients gives minus rho g over here. So that's a way of defining P prime, and if you take that definition, what that does for you is it drops out the pressure from the Navier-Stokes equation. So now we would get dp prime dr is simply equal to 0, and dp prime d theta is also equal to 0. So we can conclude that this variable total hydrostatic pressure, which combines the effects of the pressure field itself and gravity, is simply a function of axial position, x. And so now we're left with something aside from these two equations, that there's no gradient in p prime in r or theta directions. We have a momentum equation, which is now an ordinary differential equation, although I haven't written it that way here. So we have mu times 1 over r, ddr of r times du dr, and that's equal to dp prime dx. And if we think about this a little more, it's interesting to note that because u is only a function of r, this left-hand side is only a function of r also. And that means that dp prime dx is only a function of r at most. But we see over here that dp prime dr is 0. So in fact, the only possible form for dp prime dx is that it must be a constant with respect to both the radial position and the axial position, which means that that's another way of saying that du dr partial differential equation over here is just an ordinary derivative. At that point we solve this equation, so since this is a constant, we can simply integrate twice with respect to r, and so when we do that we get the general solution that u is 1 over 4 mu p prime dx times r squared, and then we have two terms with constants. We've got c1 times natural log of r, and we have c0. So why don't you take a moment to verify that that's the case before we continue. So here's our velocity solution. We get the constant c1 and c0 by considering the boundary conditions. We have two boundary conditions for a second order ordinary differential equation. The first is that the velocity is finite at the center line. And we say that because we have a natural log term which goes to minus infinity when r is 0. So the consequence is that the constant c1 must be 0 also. And then our second boundary condition, the no-slip condition at the wall, means u should be 0 when we reach the outer radius r. So if we substitute that into this equation, we get that the constant c0 just has to be minus this evaluated at capital R. And I'm going to write this then as c0 as r squared over 4 mu times minus dp dx. I write it this way because we expect that a negative pressure, that is where p prime is higher when x is 0 and lower when x is L, or anywhere further downstream, that's what's going to drive positive flow. And so we expect that c0 should be greater than 0 when dp prime dx is less than 0. And that gives us this velocity distribution. When we substitute c0 in, I'm going to pull out this term r squared over 4 mu times dp prime dx minus dp prime dx, and then that's multiplied by a parabola. So here we've got 1 minus the radial position divided by the total pipe radius squared. So that parabola looks like this. It goes from 0 at the pipe wall, higher and higher and higher until we reach the center line, and then back down again. It's symmetric around the center line. Note that this parabola is actually a little pointier than you might tend to draw if you were just sketching it by hand and not thinking about the shape of a parabola. It turns out that the maximum velocity then has to be on the center line, and we'll see in a second that the maximum velocity is twice the average velocity, that is velocity averaged over the cross section. Now we can look at the shear stress. The shear stress component we're interested in is tau Rx, that is shear stress on a radially oriented plane, resulting in force in the x direction. So this is the main drag force within the flow field. For a Newtonian incompressible fluid, that shear stress is mu times the velocity gradient of axial velocity in the r direction plus velocity radial velocity derivative in the x direction. This first term is simply 0 because second term is 0 because ur is 0. And the first term, we can take the derivative of this expression with respect to r, so this term doesn't come into play, but minus 2 times r over r squared multiplied by this expression here. So that gives us, in the end, minus r over 2 divided by minus dp dx. And since dp dx is negative for forward flow or downstream flow, then the shear stress sign is negative in the positive r direction, and positive in the negative r direction is just radial with or linear with respect to the radial position. So I've drawn that as a function of radius over the pipe radius here, and then as a function of on this side, how does that relate to the wall shear stress. So we see with this linear shear stress that the maximum shear stress will be at the wall where little r becomes big R. So wall shear stress is then capital R over 2 times dp prime dx. We can integrate the velocity profile to get the volume flow rate, which will allow us to do a pressure versus a pressure gradient versus flow rate calculation. So we integrate the velocity u over the area, substitute our velocity profile to do that. Pulling all the constant stuff outside of the integral, we're simply integrating this parabola from 0 to the outer radius times r dr. This integral comes out to be 1/4, and so the final expression for flow rate is pi radius to the 4th power over 8 times mu, and then times the negative pressure gradient. And we can substitute then into this equation what we call the pressure drop. So considering that flow is driven by a negative pressure gradient for positive flow, we'll define the pressure drop as delta p prime is equal to p prime at the entrance minus p prime at length L, and then dp prime dx or minus dp prime dx is then delta p prime, because this is oriented towards negative pressure gradient. So minus dp prime dx is delta p prime divided by the length difference, L minus 0 or L. The other thing we do is substitute diameter is 1/2 of radius, and so our constant changes from 1 over 8 here to 1 over 128. So this is a much more common formula. When you know the pressure drop and you want to know the flow rate, you have Q is pi delta P diameter to the 4th power divided by 128 times viscosity times L. Or if you want a certain flow rate and you want to figure out what the pressure drop should be, then you can quickly solve using this equation. You'll get delta P prime is 128 mu times L times Q divided by pi d to the 4th power. So it's interesting to note that this flow pressure relationship is obviously very sensitive to the diameter of the pipe. That's taken to the 4th power. Everything else in this relationship is linear. So flow increases linearly with the pressure drop, or decreases linearly with increasing viscosity or with increasing pipe length. I mentioned average velocity a little earlier. We're talking about the area averaged velocity across the pipe area or cross section. We'll note this is capital V bar, but often we'll simply use capital V to denote average velocity in a pipe flow. That's simply the flow rate over the cross-sectional area. So if we substitute that in, we'll get that that's the radius squared over 8 times mu times the negative pressure gradient, or times delta P prime divided by L. Then the maximum velocity is taken simply by evaluating the velocity profile at 0. That turns out to be radius squared over 4 mu times the negative pressure gradient, and so we see that this is simply twice the average flow rate, so that's a very convenient constant to memorize. And again, this is for circular pipe flow. So let's run a couple example problems. The first one is one from biomedical engineering. We're very interested in the shear stress in something like a heart-lung bypass system. So heart-lung bypass is essentially a pump system that takes flow out of the heart and runs it through an oxygenator and then back into the body, and that allows surgeons during open heart surgery to stop the beating of the heart while they repair or bypass diseased blood vessels, and then it's the oxygenator that's bringing oxygen to the blood and keeping the patient alive during the surgery. Now this type of circulation of the blood through a machine needs to be done carefully to avoid damaging blood flow components, and so as we run the blood through this machine, we want to keep the shear stress at a reasonable level. So that's done by controlling the relationship between flow rate and the diameter of the tubing. So here's a set of specs for a heart-lung machine bypass tubing. We have about 2.5 meters of tubing. We need a flow rate of about 5 liters per minute for a typical patient to keep the body alive during this surgery. And then the density and viscosity of blood are given here. Blood is a non-Newtonian fluid, but at reasonably high levels of shear rate, it can be approximated as Newtonian without losing too much accuracy, and the viscosity of blood is about 4 times the viscosity of water. Diameter of tubing for this design is about 1 centimeter. And if we relate the flow rate to the pressure gradient, we can see that having this set of dimensions demanding this flow rate, we can go ahead and figure out what the pressure gradient should be. So let's use this formula that we just derived, and we'll solve that for the pressure gradient. So we see the minus pressure gradient is 128 mu q over pi d to the 4th. Then we've just derived the shear stress as a function of the radial position, and we'll evaluate that at the pipe wall where it's at a maximum. And so at the wall, that maximum is going to be the radius divided by 2, or diameter by 4, times the negative pressure gradient, which we've just solved for over here. And so that's then d over 4 times 128 mu q over pi d to the 4th. Or 32 times viscosity times flow rate over pi d to the 3rd power. So we see also that the wall shear stress is very sensitive to the diameter. Let's go ahead and substitute the numbers. So here we've got viscosity, here we've got flow rate, and we have to make sure we're going to carry units. So the units are in here, and then diameter down here. And if you solve this and reconcile the units, you'll end up with 2.97, or about 3 kilogram per meter second squared. Let's check those units. So a kilogram per meter per second squared is a Newton, kilogram meters per second squared, divided by meters squared. So that's pascals. So that's the right unit, or a correct unit, for the wall shear stress. And that turns out to be a reasonable shear stress. In a typical artery, the wall shear stress is around 1.5 pascals. So this is a little higher than normally would be found in the body, but it's quite reasonable and is unlikely to damage the blood as it flows through the tubing. Our second example is a little bit different. You could say that in our first example we were ignoring gravity. I didn't mention that, but we're using P prime, so that's a way of ignoring gravity. And that was just an intermediate step to get the wall shear stress. So it turned out that gravity didn't really come into play in this problem, even though the pressure field might be different if we consider height variations in the tubing. The shear stress is predicted to be exactly the same. Here's a system where we imagine that we have some kind of a manufacturing process that involves dispensing sugar syrup, and we decide to do that rather than using pumps simply by using gravity-driven flow. So let's imagine we've got a tank with the sugar syrup in here that we're maintaining at some temperature so that it has these properties. Density is a little higher than water and the viscosity is much higher than water. This is about 100 times more viscous than pure water would be. And so in that tank then the sugar syrup is delivered through an entrance into a pipe or a tube, and then that's going to be dispensed at the bottom onto some kind of moving or conveyor belt of sticky buns or donuts or something like that. And so based on this configuration, we've got very slow velocities up here and then fast velocities going through this tube where the cross-section is small. We're interested in finding the flow rate in this configuration and whether it should be fast enough for the process that we're trying to feed. And so most of the pressure drop, most of the resistance to flow is going to just take place within this pipe. So in order to find the flow rate, we're going to again use the pressure gradient versus flow formula. Here I've written in terms of pressure drop, so delta P prime. This is total hydrostatic pressure, and then we've got diameter, viscosity, and length in the formula. I've got coordinates over here, a z coordinate that I've decided I'll start at the bottom. So our reference point is at the exit from this tube, and the tube runs in the x direction. That's the flow direction, so we've got x in the opposite direction of z, which is fine. So setting z equals 0 at the tube outlet, and then noting that essentially the pressure at the bottom of the tank can be set by hydrostatics because flow is slow out here. We would say P1 should be rho g h. H is the height of the tank. We have atmospheric pressure up here, atmospheric pressure at the bottom, defined by air. So if we evaluate P prime at the entrance to the pipe, we should have the P1, that is rho gh plus rho g times z at this location 1. So that turns out to be then rho gh plus rho gl, the distance from the bottom of the pipe to the top. And then the hydrostatic pressure at the bottom, that's P2 at the bottom times rho g z2. P2 again is atmospheric. We'll use gauge pressure, and so that means that both of these terms are 0. So in the final analysis then, the driving pressure difference, delta P prime, is simply rho g h plus L. So delta P prime represents the total hydrostatic pressure really that's going to drive flow through this tube, and that includes both the effect of tank height, rho g h, as well as the effect of height difference along the tube, rho g L. So that's our driving pressure difference, delta P prime. We just substitute that into our pressure flow relationship, so there it is. And when we put numbers in, so we've got our density 1200, acceleration of gravity here, total length h plus L is 1 meter, and here's diameter again taken to the 4th power, and then mu on the bottom, 0.7 meters, the length of the tube where this tube is providing the resistance to flow, rather than the total hydrostatic pressure difference length, which is 1 meter. We've got 0.7 meters here, and then the constant 128. And so if you work that out, this will be 2.58 times 10 to the minus 6 if you carry this through in SI units and simplify things. And so I've converted that to milliliters per second, which is a convenient set of units, so that's cubic centimeters per second, in other words. Now, once we have the solution, it's a good idea to check if the solution is valid, and that's really answering two questions. The first is to check if flow is laminar, so you'd want to check the Reynolds number. Is it less than 2300? The second is the flow by and large fully developed? And so if we go back to the picture, if the flow is fully developed, what we're really saying is that the entrance region in the flow in this pipe should be much less than the total length of the pipe, so that we can use the fully developed flow model because that covers most of the pipe length. So we want to check those two things out. So let's go ahead and look at that. To do the calculation, we need to get the average velocity coming through the tube. So we take our flow rate, divide it by the area, and that gives us about 13 centimeters per second for the average velocity. That will then go into our Reynolds number calculation. So remember, Reynolds number, that's rho times average velocity times d divided by mu. And when we substitute the properties into the Reynolds number equation, we find that the Reynolds number is approximately 8. So that's much less than 2300, and so we can make the assumption that flow is laminar without a problem. To check if flow is fully developed, we're going to calculate the entrance length. So entrance length was given early on in this talk. It's 1/2 plus 5% of the Reynolds number based on diameter, and that quantity, which is dimensionless, is multiplied by the pipe diameter d. Using a Reynolds number of 8, the second term is simply 0.4, so we get 0.9 times 5 millimeters, or 4.5 millimeters in a tube that you'll recall was 0.7 meters long. So this is definitely much smaller than the total length of the pipe, and so it's reasonable to use a fully developed model to estimate the flow rate in that case. So flow is valid. If you were to leaf back to the first example, you might want to also go ahead and check for that flow rate whether the flow is indeed laminar in that tube, and you'll find that it is. So that assumption was okay there, and then same thing, you should check to see for that length of tubing whether flow is fully developed. In that case also, that you'll find that checks out. So that should be a regular part of your engineering process, is to make sure that you're checking that you're using the right solution for the right situation. So these two examples concludes the circular pipe flow, laminar flow section of this talk. The remainder of this recording will be about flow between parallel plates. So for flow between parallel plates, we now have a two-dimensional geometry. We consider steady and incompressible flow from the left to right, and we'll again make the assumption that flow is fully developed. Fluid is Newtonian, and the flow is laminar. In the case of parallel plates, what that means is the Reynolds number based on the gap width between the plates should be less than 1400, because the geometry is different. In a parallel plate situation, you don't have sidewalls sort of on this side or the back side that have any effect on the main flow field, because the sidewalls are just so far away compared to the width of this. So there's less of the effect of this solid surfaces here to stabilize the flow. So the Reynolds number for transition between parallel plates is somewhat lower than in pipe flow. We normally, if we have some other cross section, we would say that Reynolds number for laminar is less than order of 1000, and that gives you a good rough assumption of what the transition Reynolds number should be. But here it's been measured pretty precisely, and it's around 1400. With those assumptions, let's now look at Navier-Stokes equation in Cartesian coordinates, and then we're going to go ahead and simplify these equations that you've been given. We're going to start again with the steady flow assumption. So, well, no, I guess I'm starting first with the two-dimensional assumption. So if the flow is driven by height difference and pressure gradients in the x direction, there's no major z-directed velocity, so we assume that this w velocity term is 0 for two-dimensional flow. And then we can wipe out each derivative of velocity in the z direction when we assume it's two-dimensional flow. So we've got 0 velocities here also for w, and dw dt is 0 because it's two-dimensional. In fact, everything in this equation goes to 0 except pressure gradient and body force. Next, when we assume that flow is fully developed, we get rid of any x-directed derivatives. And so that goes for any x-directed velocity derivatives here, so du's dx's and dv dx's are all 0. So that knocks things out on both sides of Navier-Stokes equations for momentum. And then since flow is steady, we're knocking out these two terms here. Now we can look at the effect of these assumptions that we've made so far on the continuity equation. So in this case, the derivative of the lateral velocity v with respect to y should be 0. So we can solve that equation that v has to be a constant with respect to y. And if we evaluate that constant at the wall of our parallel plate flow, then we realize that v velocity should be 0 everywhere. So again, consequence of fully developed flow, there is no lateral velocity in the flow field. And so that then wipes out any v multiplying terms. So at this point, the entire left-hand side of the Navier-Stokes equation is 0 in a fully developed flow. And on the right-hand side of the v velocity equation, we simply have, again, the pressure gradient balanced against the body force, whereas in the x equation we have one viscous derivative term left. And then we have body force and pressure gradient. So let's write down our simplified flow equations. The flow is purely axial, so we've got u is non-zero, but v and w are 0. And in the case of gravity being the only body force, we could write again pressure as a combination of hydrostatic pressure plus the pressure gradient in the flow direction as dominating or defining the pressure field. So if gravity is the only body force, again we'll define total hydrostatic pressure, P prime. So this is the same format that we used in the pipe flow previously. So typically we have P prime is P plus rho gz, where z is the direction of gravity, although it could be rho g and some other direction if you have a tilted parallel plate situation. So this is just the most straightforward version of things. So now the momentum equation in the flow direction is simplified to mu times d squared u dy squared is equal to the pressure gradient. Since velocity u is not a function of position because it's fully developed, it's not a function of x coordinate, and it's not a function of z coordinate because it's two-dimensional, this left-hand side can only be a function of position y, the lateral position. Whereas P prime is only a function of x at best, because the gradient of p prime in the y and the z directions, those are 0 from the other two momentum equation. So again, we conclude that this term dp prime dx must be a constant. It could only vary with x, but u doesn't vary with x. So this is now an ordinary differential equation, and we can integrate it twice. So with that second integration, we get the following. We get 1 over 2 mu, the pressure gradient dp dx times y squared, and then we've got constant c1 times y, constant c0. Let's consider the case if this is the x direction, we start y from the bottom plate, and the case of both plates being stationary. So the upper plate velocity is u is 0, lower plate is u is 0, and so our boundary conditions will be no slip at the upper and lower walls. And again, the flow could be pressure driven or gravity driven or both. If the gap width between the plates is a, then we'll find that the solution when we evaluate the constants is a squared over 2 mu times the negative pressure gradient times this parabola y over a minus y over a quantity squared. So I'll give you a moment to, well, you should take a moment to pause the video and verify that this equation is the equation you get when you evaluate C1 and C0 with 0 boundary conditions at y equals 0 and at y equals a. And then moving along, we write it in this form again, noting that the flow is driven by a negative pressure gradient. So for u to be positive, you could say it's a consequence of this equation. This parabola written in this form is always positive between y is 0 and y equals a when this pressure gradient is negative. So we can see forward flow driven by negative pressure gradient. And negative pressure gradient simply means that pressure here is higher, pressure down here is lower. Right? So that should make physical sense. We push on this side of the fluid, and the result is motion in this direction, resisted by the viscosity here of the fluid. We also note that velocity is more sensitive to the gap width a than any other parameter in the problem, and we'll see that when we also solve for the flow rate q. It's often convenient to use coordinates that are relative to the centerline position. So if we define y prime as y minus a divided by 2 and we transform the coordinates, then we'll get that the velocity u is a squared over 8 mu times the negative pressure gradient and then times 1 minus y prime over a divided by 2. So this is very similar to, in fact, it's the same shape that we saw for pipe flow, a parabola that's 1 minus this length scale squared and divided by what you would call the radius, which is half of the gap width, a over 2. But because we're in a two-dimensional geometry now, this constant a, well, the constant the constant out front is actually the same in this situation as it was in the previous. Now we should take a look at shear stress and flow rate. These are very useful formulas that can be derived from this velocity profile. So the shear stress is that we're interested in is tau yx, that is tau on a y-facing plane giving a force in the x direction. For a Newtonian fluid, that's viscosity times dv dx plus du dy, and then the only term that shows up for fully developed flow is du dy because v is 0. So we substitute the u velocity, we take that first derivative, and we end up with tau is a over 2, the negative pressure gradient, multiplied by 1 minus y divided by a over 2. Or if you use y prime, that'll just be times y prime over a over 2, but it'll be minus, so minus y prime over a divided by a over 2. And then the flow rate given per width that is into the z direction, q over L, is given by the integral from minus a over 2 to a over 2 u times dy prime. So dA is dy prime times this length times this thickness into the page L. And so this looks like flow in a pipe, but here the constant is different because it's two-dimensional. So the constant of integration is going to be 2 over 3, so that we end up with 1/12 out front. So the gap width cubed divided by 12 times mu times the pressure gradient, negative pressure gradient. We can then rewrite that as flow rate versus pressure drop. Again, we've normalized things by L, so Q over L, that's the gap width cubed times the pressure drop from inlet to exit divided by 12 mu L. Capital L is the length of these parallel plates. The average velocity is going to be flow rate divided by cross-sectional area, so Q divided by A times L, so that's A squared over 12 mu times the negative pressure gradient. And the maximum velocity is velocity evaluated at the center line, and that turns out to be 3/2 times average velocity. So take a moment to verify that this goes along with the velocity profiles that were derived and the flow rate that's been derived here. So then continuing along, we can also consider the case where one plate is stationary and the other plate is moving at a velocity capital U. This is a model for things like the flow that takes place inside a bearing, so certain types of lubrication flow. And if you were to solve the problem, it's a linear problem, and so you could use superposition. That is, you can sum together the solution that we just derived for a given pressure gradient dp dx. That gives us parabolic flow. And then you can add to that the solution that we saw quite a while ago for a Couette flow. That is the flow driven by the upper plate. So if you superpose those two solutions together, you'll get some kind of a linear plus parabolic. For the case where pressure is higher upstream, lower downstream, and the upper plate is moving downstream, we get a parabola that looks kind of like this. So this is a negative pressure gradient driving flow this way, so that pushes the velocity profile outward off of a base of the Couette flow over here. For the converse case, if we had higher pressure here, lower pressure there, then we've got some back pressure acting against this Couette flow, and so the velocity profile might look sort of like this. And in fact, you might get then negative shear stress on the bottom that is pushing backwards on this plate, and then positive shear stress on the top plate over here. So let's now look at two different examples. The first one would be that we have a pneumatic tube, and we have some kind of a cylinder in the pneumatic tube delivering something like, you know, dollar bills or checks in a bank, or delivering medicine within a hospital. These are a couple of common uses of the pneumatic tube systems, just to physically deliver stuff around a large building with a tight organization of some type. So let's assume that this delivery cylinder is 20 centimeters long. We're moving it at a velocity of 2 meters per second, and our radius is about 3 centimeters, so this is more of sort of pharmaceutical sized delivery tube. And then there's a small gap of width 1 millimeter between that cylinder and the wall, and we want to figure out what the shear stress is that would be slowing down this mass as it's moving through this tube. On this next slide, I've sketched in a couple of things. One is just a picture of the mass for purposes of free body diagram, and the other thing is the flow that we're analyzing, which is the flow in the gap between the mass and the wall of the tube. So the gap width there is A. Now, just a quick remark, this is a narrow gap compared to the radius, and that allows us to ignore curvature effects. So we treat this as flow between infinite parallel plates with a length extent in the third dimension that's equal to the perimeter around this tube. And so that allows us to avoid some of the complications that would happen if we went with a cylindrical coordinate system, and the price in terms of accuracy is quite small. So that configuration then becomes a parallel plate at the top, moving with velocity capital U. That's the velocity of this mass in the tube. And then the lower plate is stationary because that represents the outer wall of the tube. Well, it's the inner wall of the tube, but it's the outer wall of the flow domain, and that one's stationary, and then the gap width is A. And then the length of this flow domain is L. That's the length of the mass or the carrier in the pneumatic tube. Let's first consider now the forces applied to this tube. We have pressure on either side or either end of the tube, so I'll call that P0 for the zero end, and so that's pushing the mass forward, and then we have PL, the pressure on the other side, is pushing it backwards. And in addition to that, because there's flow in this gap, we have shear stress, tau Rx, applied to the tube. We think since this is moving forward, that shear stress should be pulling backwards, although it also really depends on pressure difference, P0 minus PL, what really happens. If we then consider a steady motion of the tube, then the sum of the forces on this mass, steady velocity of this mass. Some of the forces in the x direction should be equal to 0, and then those forces are, we've got a pressure force from P0 on the left hand side, that's positive, so P0 times the area pi r squared, and then on the other end we have a negative force, so minus PL, and again same area, and then we take the shear stress on the surface of the mass times that surface area, that's 2 pi times radius times length, and so the sum of those is equal to 0. And in terms of the flow problem that we've looked at, flow in the gap, we'll rewrite that as P0 minus PL is delta P, the pressure drop from this end to this end of the gap, so we've got delta P times pi r squared, and then we move this to the other side, that's got to be equal to tau Rx times the lateral surface area, 2 pi r L. Now if we think about the general solution for flow in this gap, it's going to have two parts. One is essentially Couette flow driven by this velocity capital U, and the other is a pressure driven flow, we call that Poiseuille flow, driven by pressure drop delta P. If the shear stress is quite low, this pressure difference might then be quite a bit lower. So let's see if we can assume that delta P is equal to 0. So we'll go ahead and we'll initially make that assumption and see what the consequences are. So if we can assume delta P is 0, then we just have a linear velocity profile in this gap, and this takes us back to the viscometer chapter, chapter 2, that the the shear stress in that gap is simply mu times velocity difference over the height difference here, so that's mu u divided by a, the gap width over here. So if we plug in some numbers, here's air viscosity and the velocity of our mass, and then the gap width, 1 millimeter. And that shear stress works out to be quite small, 0.036 pascals. Now what I'm going to do with this, we can estimate the force resulting from this shear stress, but first let's take a look at what delta P should be based on equilibrium considerations and see if we can ignore delta P. So the shear force that results from tau Rx is tau Rx times the lateral surface area 2 pi RL, and if you plug in the numbers we get essentially a millinewton or so, which is quite a small force. So the shear drag that's slowing this down because of the velocity of the mass is quite small. That in turn drives a pressure difference, a delta P of this shear force divided by this area, so F shear over pi r squared. The area is quite small also in SI units, so that boosts this up to a pressure drop of 0.48 pascals. And you might look at that and say, well, that seems quite high if we compared it directly to tau Rx, but how does it affect the velocity profile? We could see that most easily by going back to the fully developed pressure-driven flow solution between the two parallel plates, and I'm going to call the shear stress just due to that pressure drop delta P, we'll call that tau delta P. So let's evaluate that. That turns out to be the gap width divided by 2 times the pressure gradient dP dx. The pressure gradient is minus delta P over L, so we get a minus A over 2 times delta P over L. And so when we evaluate that, because A over L is quite small, we get a very small shear stress, 0.0012 pascals. And we'll see in a second that acts negatively compared to this direction right here. So returning to this question, can we ignore delta P? Well, since the shear stress due to delta P, due to the flow driven by delta P, is quite a bit less than the tau Rx that we got from looking at U, in fact, we're okay. We could ignore it in this case. So I'm going to sketch in the velocity profile that we expect to see. Here's the model that I use to calculate tau Rx, which just is a linear velocity profile. So it says flow is really just driven by the motion of the mass, giving us a velocity u. And if we also considered the effect that there's a pressure gradient, what does the pressure gradient do? So we have a higher P0 compared to PL, overcoming this shear stress. And then the magnitude of that, though, leads to a very small change in the shear stress. So in fact, if we were to look at that velocity profile, I've drawn it in red. This is the velocity profile including the effect of delta P, and you see there's very little change in the wall shear stress. The slope over here is barely changed. In fact, I am overemphasizing in this sketch the magnitude of the effect of delta P in this case, just so you can see the two lines, because in fact this is well less than 10% of an effect on the slope over here. So you would barely be able to see the difference between those two lines in this particular case because the load demands are quite small. So let's look at another situation. The reason the loads are small here is because this is moving horizontally. What if we're moving vertically instead? Let's say we're moving against gravity, so we need to go from the first floor of the hospital to the third floor of the hospital to deliver some medication to a patient up there. And so in that case, the mass, our carrier in this tube, is moving against gravity, And so the different forces here have to overcome the weight of that mass. So let's look at the same thing again. We're going to have the same gap width, radius, desired velocity here, length of the tube, and we include a mass now of 3 kilograms. So here we have our mass again, and when we consider the forces applied, we've got again the pressure on the downstream end or down motion end, and lower pressure on the other end. Shear force due to velocity in the gap, and then the mass mg. And so compared to last time, that mg term adds in here with the shear stress, and so we say, can we assume that delta P is equal to 0? In this case, mg is being so much greater than the shear force that we just calculated. It's 2 orders of magnitude greater, so the answer is no, because this pressure difference is going to have to provide for that additional mass. So compared to the last velocity profile that I sketched in there, we expect to see something that looks more like this. You have the same linear profile, and then because delta P is much bigger, that basically pushes this velocity profile way out. In fact, we might go from a negative shear stress on this surface to a positive shear stress if delta P is big enough. It really depends on how big mg is, how that results in a certain amount of pressure difference. So then we might have both a combination of extra pressure here and some shear stress moving the mass upwards in that case. So I welcome you to work ahead on this if you like, but we're going to go through this in class when we meet on Wednesday. And then after we cover that example, we will also work on a related example, which would be what happens if you decide to stop the mass by closing off the end of the tube. And this model, in addition, is a model for a automotive crash sensor that's based on a mass held by a combination of a spring and air pressure within a tube. And so that'll be our second example, and this one you've got in your handouts. The previous one you don't, but I'm going to post that page so you could print and work with it if you feel like it, and I'll bring some copies to class for you to work on Wednesday. So that concludes this first recorded lecture,